So let's conclude by doing a summary of the different matching strategies that we have, just to further solidify the concept. So to start out, we have series matching. So to draw a little cartoon or a miniature version of it, what that means is that over here you add this extra resistor so that you have a perfect match on the generator side, and you're doing it in series. So you add that little buddy there, and so the good thing about that is that it's power efficient, just like what we mentioned before or later when we looked at parallel matching. You don't have a situation where you're dropping a boatload of voltage across one of the resistors. But on the flip side, one of the biggest issues is that ZG might be a function of time. So that makes it kind of hard to actually implement in reality. The other drawback that's also subtle potentially is that if your generator, your source impedance is really low, this is a fairly sizable resistor. So you actually lose a lot of voltage going into the transmission line. So you also end up having a lower VL on the other side because you're dropping a lot of that load on this series match here. Second is the parallel match. So you say, let's just try to solve this on the load side instead. And so you keep the generator side the same, still have your transmission line, but now you have an impedance that you've cleverly chosen to put in parallel with the load such that the two parallel together will be equal to Z0. And the good thing about this is that it's pretty easy to implement. You just slap another resistor in there, but then at the same time, one of the things that we saw was that it's power inefficient, because what ends up happening is that you end up throwing a fair amount of power out of this parallel match resistor. So one improvement that you can do with that is you keep everything the same with your parallel match, but you also add a little capacitor in here. And then what that does is that in the beginning, this is a short, you do drop a lot of power off of here, but then you have a really good match, and over time, once the reflections die down, this capacitor charges up, and then all the power continues to go through ZL. So it's also pretty simple. The main weakness of this approach is that you're still losing power, at least in the beginning. So you're still dealing a little bit with the problem of the parallel matching, but only for the first little bit, so it's still a little bit better. But you also have more components and more complexity as a result of it by requiring you to throw in that extra capacitor. And then the other clever approach that we talked about was that you put a little couple set of diodes, this one going up to your rail voltage at the load. And so what that does is it ends up capping your voltage, and so even though you might have a reflection, it puts an upper limit to the size of that reflection. So the nice thing, I guess, for the purposes of this class is no math. We're just describing it and moving on. But the problem is that you're not really fixing the situation. You're not solving the reflection issue. And so if you end up, I'll just talk while I spell reflection properly. But if you end up having a poor match on the generator side and you still have a lot of reflections bouncing back and forth while you're limiting the size of it, it still might take a while for it to go away. This is just a quick summary of the 4 approaches that we talked about. I think that if you have a general idea of how to implement these, as well as know how to calculate the power in the transmission line throughout different locations in different times, then you should be in pretty good shape for this chapter.